talking about analyticity of harmonic functions. In the first part of this lecture, we have proven theorem 1, stating that if U is harmonic in domain omega and continuous in the closure of omega, and if we consider a subdomain, so domain omega 1 inside omega, such that distance from omega 1 to the boundary of omega is non-zero, then for any point x in omega 1, we have this estimate for derivative of order alpha of our function u, and in terms of n is dimension of our space, k is related to the order of derivative, and rho is the distance, and here we have maximum of absolute value of the on the boundary of domain omega. So then we will be using these estimates. Okay, so our second theorem discusses real analyticity of harmonic functions. So assume that U is harmonic in the domain omega, and then we can say that U is real analytic in omega, which means that for any point x0 in omega, U of x has a representation as a convergent power series in some neighborhood of that point x0. Okay, so let's start the proof. So we know that harmonic functions, they can be differentiated as many times as we wish. So if we want to write down Taylor formula, we will be able to compute derivatives, and we will be able to compute coefficients. So here I wrote Taylor formula in slightly different form compared to the version that we had in part 1, where I used differentials, but I believe it will be clear how to switch from the form written in differentials to this form. This form uses multi-indices, so then it will be derivative of order alpha of U alpha factorial x minus x0 alpha, and here I explain what again the notations related to multi-index, and here this I mentioned that this is Taylor formula, so we have here terms of different order, less than order m, and this term we have here a remainder written in the Lagrange form. And so we have a point, so everything is written in the neighborhood of point x0, so x0 would be, we can consider center, a ball with the center at x0, and both x and x tilde belongs to the ball, centered at x0 and with radius rho, and rho is a positive number, but it is relatively small, so such that ball with radius as twice as big as rho is still in the domain omega. And our goal is, so what does it mean? We want to show that Taylor series is convergent. We need to prove that the remainder goes to 0. So our goal is to show that Rm approaches 0 as m approaches infinity. And here we will be proving this when we assume that distance between x and x0, so we will be considering formula for such x that are within the ball of radius epsilon, and epsilon is a small number, so it's smaller than rho, and it's possible to choose epsilon in such way that epsilon does not depend on m. Right, so that is our goal, to prove that remainder goes to 0 as m approaches infinity. And first let's do some auxiliary computations that we will need. So first let's look at this expression, right? We can think of this as using a Taylor formula, rewriting it in this form, or we can see that what it will be something to power m, so it will be just polynomial, right, of degree m. If we will be using Taylor's approach to rewrite it in this form, for instance, we will be differentiating, right? It doesn't matter with respect to which variable, but still when we differentiate, everything will be multiplied by this term. And if we think of this as an expansion centered at point 0, we will see that only terms of this order m will be present. So we can have this formula. So why do we need this formula? From this formula we can get another one. So if we set here all variables x1 and so on to be 1, then here we will get 1 plus 1 n times, so it will be m to the power m. Here we will have m factorial, and here, so we will just have the sum of 1 over alpha factorial. Right, so we will use this formula in a second. So in our derivation we also will use the estimate from theorem 1, and having this in mind, we can write estimate for u at point x tilde. So now we have, instead of k in the theorem 1, now we have m, so we replace it with m, and we can write that maximum u is taken within the closure of the ball centered at x0 of radius to rho, and that would be for alpha order of alpha equals m, and x tilde in the ball of radius rho. And then we can write, so we have this to estimate a remainder. Let's write the whole thing. So for estimating remainder, we need to take this estimate, right? So we copy this part, and then it will be multiplied by absolute value of this term, and we have sum of 1 over alpha factorial, so we have it here. And then this term, sum of 1 over alpha factorial, we can replace using the formula we just derived. So here I just copied everything. So this term, instead of this sum, I put m to the m over m factorial, and the rest of the terms I just copied. And then we can write from here, we can rewrite slightly different. So here we have m to the m, and here we have m to the m. So it will be m to the 2m, so I put here n squared, and m here, then x minus x naught I also put here and draw. So this whole thing would be to the power m to the m, and I just wrote separately m to the power m and m factorial because I'm going to use a Stirling formula to simplify it further. So here is the Stirling's formula written in the form that is convenient for us. I will not be talking about the derivation of this formula at the moment, but there is such a formula. All right, and then here I just copied the inequality that we had on that board, and so now we will use the Stirling's formula to replace this term with e to the m, and then we will have the following estimate. We will have m squared e times x minus x naught, distance between these 2 points overall, everything to the power m, and maximum of absolute value of function u over the closure of the ball. And then next step, so if we take x at the distance that is less than epsilon, and epsilon is chosen in such way so that we have this whole thing less than 1. This is obviously possible to do, and then in this case we will have for our remainder the following estimate, right? If we just replace x minus x naught as distance with epsilon, we will have this, and then we can see that if this number is less than 1, then to raise to the power n it will be getting smaller, and so what we will have is that remainder will go to 0 as m approaches infinity. Right, that's basically what we want. So we can just say it again, that if we look at the ball centered at x naught, radius epsilon, when epsilon is less than rho O n square e, then if we just find the difference between our function u of x and this part of the Taylor series, it's obviously would be equal to the remainder, and remainder goes to 0 as m approaches infinity uniformly with respect to x and x tilde, and that means that this difference will go to 0 when x minus x naught is less than epsilon and x tilde is in the ball centered at x naught of radius rho, so which means that our function u of x has Taylor expansion, so Taylor series convergent. This finishes the proof. Okay, so we just established that harmonic functions are real analytic functions. So now I want make maybe a remark in the form of theorem of how we can continue real analytic function into the domain, into the complex domain. So we can think of our harmonic function, which is real analytic function of, say, n variables, and they all are real, and then we just give each of the variables x1, x2, xn. To each of the variables we add small imaginary part, right? So think of that. So now analytic continuation. So let u be continuous in the closure of domain omega and harmonic in omega. So then we will continue. We will consider domain omega 1 that is belongs to omega such that distance from omega 1 to the boundary of our big domain is not less than 2 rho, and rho is a positive constant. And then you can be analytically continued to the complex values when we take every x and xj and add to it I, y, j. X is our real vector, y is also our real n-dimensional vector, and so we are continuing from domain omega 1, we continue to the domain which we call here b delta by adding some small imaginary parts to each of them, where x belongs to omega 1, and we can say modulus or magnitude of vector y is less than delta. And delta can be written in terms of rho, and this comes from the theorem 2, rho over 2n square e. And then also for this function u of x plus iy, the following inequality holds. So we can say the supremum of absolute value of u in this our complex domain is less than or equal than 2 times supremum of u in omega. And so the proof, we use essentially here theorem 2. So we know that from theorem 2 that function u of x can be expanded into Taylor series at point x0 in omega, and radius of convergence would be no less than rho over 2n square e if the distance between x0 and the boundary is no less than 2 rho. And we obtained estimates for the remainder, and now what we can write, if we write the expansion, right, for u of x, we'll write its Taylor expansion, and then from the estimates we know that this series will have a majorand, right? So each term, so the whole series can be replaced with this series if you look at the theorem 2, and then we can see that for if x minus x naught belongs to the ball of radius rho over 2n square, then for u of x, for absolute value of u of x, we can write that this is less than or equal than 2 maximum value of u over the closure of the ball centered at x0 and radius of 2 rho. And then we can say that this formula, our Taylor series, that was derived in theorem 2, well, not derived, discussed, right? So this formula can be defined for complex values of x as well, when the following inequality holds. When sum of xj minus xj naught squared to the 1/2 less or equal than rho over 2n square e, we call this number delta, and for such x we will see that this inequality holds, and this series defines and analytic functions of complex numbers in this domain b delta, when x is our real vector and y is our real vector. So we can talk about analytic continuation to the complex domain for harmonic functions as well. Thank you.